Welcome to the first video on surface integrals where the surface is given explicitly. For a surface S given by z equals g of xy that is continuous and differentiable over the region R on the xy plane, we can evaluate this double integral of f of x, y, z integrated over the surface S as the double integral as we see here over the region R in the xy plane. And there are some important things we should notice here. First, we're going to replace z with g of xy, and second, differential s is replaced with this extra integrating factor here, and then differential a written as dx dy or dy dx. And notice in the previous video when we were talking about surface area, we introduced this surface integral here where f of x, y, z was equal to 1, but now the integrand is a function other than 1. Let's take a look at where this integrating factor or this Jacobian comes from. So in the previous video we showed how to determine the surface area of a parameterized surface using this double integral here on the right. Well, if we have z equals g of xy, then our vector valued function for the surface would be x, y, g of xy. And so the partial derivative of r with respect to x would be here, and the partial derivative of r with respect to y would be here. So if we determine the integrating factor here, the magnitude of the cross product, this would be the cross product of our two partial derivatives, and then the magnitude does give us the Jacobian or the extra integrating factor that we saw on the previous screen. Let's go and take a look at our first example by looking at an application. Here we have a roof given by the graph of g of xy over the following region. If the density of the roof is given by f of xyz, determine the mass of the roof. So if we integrate the density function over the surface g of xy, this will give us the mass. So let's take a look at a graph of actually what's happening in this situation. The surface of the roof would be the purple plane, and the given region is bounded by these yellow planes. So if we integrate the density function over this purple surface, it'll give us the mass of the roof. So let's go ahead and set this up. The mass is going to be equal to the double integral of f of x, y, z, our density function, integrated over the surface S, which is going to be equal to the double integral over the region R of f of x, y, g of xy, which is 25, plus, I'm going to write this as 1/2 x plus 1/2 y, times our integrating factor of the square root of 1 plus the partial derivative of g with respect to x squared. And here's g, so the partial derivative with respect to x would be 1/2. So we're going to have 1/2 squared plus the partial derivative of g with respect to y squared. That'll be 1/2 squared as well. And because the integrating region R is rectangular, the order of integration doesn't matter. Let's go ahead and integrate with respect to x first, and then y. So limits of integration with respect to x will be from 0 to 40. And for y, they'll be from 0 to 20. Now let's take a look at this integrating factor here. 1/2 squared is 1/4. So we have 1 plus 1/4 plus 1/4, or 4/4 plus 1/4 plus 1/4 underneath the square root, which is going to be the square root of 6/4. And the square root of 4 is equal to 2, so we have square root of 6 divided by 2. Let's go ahead and factor that out. And now for our function f, we'll have 150 minus 2 times z, but z is 25 plus 1/2 x plus 1/2 y. Now let's go ahead and clear these parentheses here so we can think of distributing a -2.
So we'll have 150 minus 50, that's 100. And then we'll have minus x minus y. Let's continue this on the next slide. Now we'll integrate with respect to x, treating y as a constant. So we'll have 100x minus x squared over 2 minus xy. And we'll evaluate this when x is equal to 40 and when x is equal to 0. Notice when x is 0, everything here is going to be 0, so we can just replace x with 40. So we'll have 100 times 40 minus 40 squared divided by 2 minus, this will be 40y. Well, 1,000 times 40, that's going to be 4,000 minus, this is going to be 1,600 divided by 2, which is 800. So 4,000 minus 800 is 3,200 minus 40y. And now we'll integrate with respect to y. So we have 3,200y minus 40 times y squared divided by 2, which will be 20y squared. Now we'll evaluate this. So we'll first replace y with 20. We'll have 3,200 times 20 minus 20 times 20 squared. And again, notice when y is equal to 0, these will both be 0. Now to save some time, I've already evaluated this. This here is equal to 56,000. So square root 6 divided by 2 times 56,000 is approximately equal to 68,585.7. So this would be the mass of that roof, and if this was a metric system, this would be in kilograms.
So again, this would be the mass of this roof in purple using the given density function. And we'll take a look at several more examples of surface integrals over the next several videos. Thank you for watching.